Hello everyone, myself Sachin and my topic is optimal binary search tree. So we are going to look into the problem definition, recurrence and an example for better understanding. So let's get into the problem definition. So before going to optimal binary search tree, you remember what a binary search tree is. Binary search tree is nothing but there's a root and everything on its left is lesser root and everything on its right greater than the node. So this is a binary search tree. For example, let's consider a binary search tree considering 2, 1 and 3. 2 is the root, left everything is less, in case 1 is less than 2, and on right everything is greater than 2. So let's move on to the time complexity of the optimal binary search tree. So the time complexity of a binary search tree, the searching in a binary search tree is log n, which is best and or average case. This complexity comes when the resistance tree is balanced. So balanced search tree is something like this. This is some of the basics of binary search tree. We have time complexity items which we have, like they're not evenly distributed, which means like you consider that, let's say the items are 1, 2 and 3 and the probability is this, of the 3 items are 80, 10 and 10. So now if you are going to calculate the time complexity considering this, so the time complexity of this binary tree, the total number of operations we are going to do is, the probability of 2 is 0.8 and the search time is 1. So when we start our search, the root is the first position, so we start from there. For 1 the probability is 0.1 and we're going to find it in 2 operations. Similarly for 3 the probability is 0.1 and we're going to find it in 2 operations. So if we are find 3, we start from 2, 3 is greater than 2, so we find 3, it is 2 operations, that is 1.9. Let's see, we create another tree which is something which is not balanced, 1. So probability of 8 coming is, for 1 is 0.8, search time is 1. For 2 the probability is 0.1, we take 2 operations. For 3 it is 0.1, we find it in third operation, so the total becomes 1.3. So depending on the frequencies of items, it can take less for an unbalanced, even if when the tree is unbalanced, and even if the tree is balanced, it might take more or longer than an unbalanced tree. And this is the whole idea of optimal binary search tree. So we take a balance, depending on the frequencies it might not be optimal. So if we define the problem like So we say that we have items 1 is greater than 2, so smaller than 2 and smaller than 3 till n, 1 to n, with their probability is p1, p2, p3, p4, pn. And then we need to find a tree which is most optimal. That means we need to find what is going to be the root, this binary search tree, out of these items, and then we keep on going and finding the subtrees and adding on the nodes. So finding the subtrees in the primary tree, so we can create the optimal tree. So if we want to find the total cost, as we did above, here the total cost came out 1.9, amount 1.3 for this tree. So then what would be the formula for finding the cost of tree, which will be if we have items 1 to n, summation n to I, that is equal to 1, p in I into the search time of I in t. That's what we did here. The probability 1 of 1, search time of 1, 2, the search time of 2, of 3, the search time of t. So this is the same formula, or what we can say is the cost of t is summation I is equal to I to n, p of I, all the probabilities, and the dip of I plus 1. So it is summation I to 1, all the probabilities, and I to 1. So if we go above, the depth is 0, the depth is 1, the depth is 2. So when depth plus 1 is 1, which is the total search time, plus 1, 2, the search, that is the total search time. So then we convert it into a depth. So this is the basic idea of optimal binary search tree, where we try to find the optimal based on the frequencies or the probabilities of items of which are coming. I'm going to end this video here, and this is about the optimal binary search tree. Thank you.